I had a go at doing a titration. It didn't work, it managed to block up. And so what I'm going to do is going to have another go at trying to do the titration of sodium hydroxide, an unknown concentration of that, against a known concentration of hydrochloric acid. And what we should be able to do from this is work out the concentration of the unknown solution. Why did it go wrong last time? It managed to block up the spout, so armed with fresh chemicals and clean equipment, we're going to have another go and see what we can do. So let's go over and have a look at the setup. What I've got here is a burette, which you can just see the bottom of there. I've got a burette. This holds 50 centimetre cube, and this is a B class rather than an A class piece of glassware, which is fairly standard for what we use in schools. And I've also got here a pipette. The pipette holds 10 mils, and the pipette we can put into a pipette dispenser. This is slightly different than what many schools use. They use bulb ones, but it's basically the same, just a little bit more posh, I suppose. What have we got? I've got my unknown solution, my unknown concentration of sodium hydroxide. I have 2 molar hydrochloric acid, and I've got an indicator which is phenolphthalein, and this goes from clear in acid to pink in alkali. I've got some conical flasks ready to start, and all I need to do is ready the pipette and ready the solutions. So let's get everything going. So my burette, I'm going to make sure this is turned off. This is the on position. I'm going to turn it off, and I'm now going to fill this up with some alkali. So I'm going to put this on the ground. We're going to use one of these funnels to help things, and we'll start using the alkali. I'm going to put alkali in the tube. We could put acid in there, we could put alkali. It doesn't really make much difference. It makes a little bit difference on what the indicator does, which way it's going to go. So let's pour some in. Right, so here is my alkali ready to go. I don't normally pour this back into the stopper solution, but in this case it's not going to matter. And I'm going to set the top here to 7 centimetre cubed. So it's set 7. The bottom of the meniscus is just on the 7, and it's easy to read from the bottom of the meniscus to the bottom. Right, so I've got my alkali ready in the burette. Now let's set up the acid in the beaker. For this we're going to use a pipette, and I'm going to take up in here 10 centimetre cubed. So I'm going to try and get this as accurate as I can. I'm going to get my head down so it's lined up with the meniscus. Take this out and then we shall put this in. I'm using the plunger to the button here to let the liquid out. It doesn't come out terribly quick. It does come out faster if I force it out. And there we've got 10 centimetre cubed. I'm going to put the lid back on the acid and I'm going to put that back safe out the way, and let's now take my phenolphthalein and I'm going to put in just 2 drops. Going to swirl it, give it a good mix, and now we can set the titration going. The first time we do this we normally do a rough titration, so I'm just going to let the titer go. We're going to put some in and we can see it's going this purple colour, and if I give it a little shake it clears up fairly quickly. Now what I can see, we're getting now towards the end, as I'm putting in a little bit of the alkali, it's becoming more difficult for it to disappear. So I'm just putting in a little bit of a time just to see how we're going. Now it's taking a little while to go, so I'm guessing we're about right, so I'm now going to add it much slower. And there we've got the end point. And what I can do is I can now read the values off on my burette to get my results. So let's see what we've got. We started off at 7 and now we're down here, and I can see the 18, so this is 17.8. So I've gone from 7 centimetres to 17.8, which suggests that I used about 10.8 centimetre cubed, and that reacted with 10 centimetre cubed of 2 molar HCl. We're going to repeat this experiment and we're going to see if we can get a little bit more accurate here. But before I do that, I'm going to show you what we can do with this solution. So I'm just going to get a pipette out and I'm going to add a little bit of this sodium hydroxide to this solution. So let's just zoom in on the solution. And what I'm going to do is I'm going to put a few drops of alkali in there, and I know I've now got to the end point. I'm going to take some acid and I'm going to bring this back until the solution goes clear. So let's take some acid, and I'm going to put some acid in here, and if we give this a shake we can see that it's gone clear. Right, now we're just going to add a couple of drops of alkali. It's just pink. I'm going to add one more drop. And there it's gone. But if I were to add just one drop of acid, it goes clear again. That's just not quite. Let's add 2 drops. And there we are, 2 drops, and it's gone clear. 1 drop of the alkali, and it should go pink. That was a small drop of acid. I'll do it again. 1 drop of acid. Really, that's the end point. And we go back to the clear. So it's accurate enough here that I can put in just 1 drop, and 1 drop tells me where we reach the end point. So we can get really accurate results with this system of doing a titration. Right, I'll move those 2 out the way, and what we'll do is we'll set up another one of these. Why do we do more than 1 titration? Very simple. It's how accurate we can try and be. So we're trying to get as accurate a result as we can. So I'm putting my head down. I'm going to make sure I get this as accurately as I can. And then we can put the acid in. I'll squirt it out because I can't be bothered to wait all that amount of time, and nor can you. There's my acid. I'll lay the pipette and its container down. I want to put in just 2 drops of my indicator. It's certainly quite strong, and put the lid on this, put it back out of the way, and we're ready to start again. Now this is at 17.8, and let's put some in. I know I can afford to put in something like about 9. So I know I can take this down to about 26 quite happily, and I've got 26 set just below here, so I can let that in. Because I've done this titration once before, I've got now a much better idea about where it's going to go. So I've taken it down to about 26. Now I'm going to put this in very slowly. So let's set this so it's going to just put in 1 drop at a time. I've got it a little bit too slow. Bit too much. Let's put in 1 drop. That was 2. Takes a bit of skill. But I want it to come in fairly slowly. Going away. I'm at 27.3. Go just a tad faster. But I don't want to go past the end point. And sometimes you just have to settle with what you've got. There's about ideal. Takes a long time and you have to be fairly patient with this. You can't rush it. If you do, you'll go over and you don't want to do that. We're getting to the stage now where it's getting more difficult for it to disappear. We're nearly there. And there is my end point. So what we can do is we can read off now on here my results, and looking at this, I've got 28.5. So we can now repeat this experiment several times. I'm not going to bother because that's going to be a bit boring for you. So let's go over it and have a look at the calculations. Okay, so what have we got? Well, we now know that with 10 centimetre cubed of 2 molar hydrochloric acid, that's going to react with, and let's do this on the calculator. So we've got 28.5 and we're going to take away 17.8. And this time we've got 10.7. You can see that my rough estimate wasn't actually that bad, and we can see that I've got 10.7 centimetre cubed of my unknown concentration of sodium hydroxide react with 10 centimetre cubed of 2 molar hydrochloric acid. Now let's see what we can do. Well, when I try to do this, I think the first place to start is, let's start with a balanced equation. So let's do that. We know that an acid plus a base, in this case it's an alkali, an acid and an alkali, is going to give me a salt, NaCl, plus water. Now we need to balance the equation. I've got one chlorine on that side, I've got two hydrogens, one chlorine, one sodium, one oxygen. It's balanced. That was a bit of luck. So I know that one molecule of this will react with one molecule of that, and therefore we know that 1 mole of this will react with 1 mole of this. But of course I don't have 1 mole, so let's work out how many moles that I actually do have. I've got 10 centimetre cubed of 2 molar HCl, and I want to work out its concentration. We want to work out the number of moles that I've got of this, and that is the number of moles equals here the concentration times the volume divided by 1000. Now I know my concentration, that's 2, the volume I've got is 10, all divided by 1000. You can probably do this one in your head, but we're going to do it on the calculator anyway. So we've got 2 times 10 divided by 1000. And that gives me 0.02 moles of HCl. So what do we know? Well, from this equation I know that 1 mole reacts with 1 mole, so in this amount of 10.7 centimetre cubed of NaOH, I know I've got 0.02 moles. So let's see if we can work out what the concentration is. N equals C times V over 1000. Let's rearrange this to make C the subject. So I will need to divide by V and multiply by 1000. So I can say that C is going to equal N times 1000 divided by V. Or, as we've got it, my number of moles that I've got, which is 0.02 times 1000 divided by the volume that we had, which was 10.7. Let's put this into the calculator. Naught point 0.02 times 1000, all divided by 10.7. And it comes out at 1.86 moles per decimeter cubed, and that is my concentration of my sodium hydroxide. We get many problems like this in the exam, and we have to be careful sometimes if we get some other things. So let's have a quick look at what sort of problems that we could get with one of these titration calculations. Let's take a different example, and this time I'm going to take some sulfuric acid, H2SO4, and I'm going to react that with, just a change, we'll do potassium hydroxide. So we get here acid and an alkali gives me a salt, which is this time going to be potassium K2SO4 plus water. Well, the reactions don't look balanced, so let's go ahead and try to balance them. I've got CBA. I can't be asked. My chemical, I've got my hydrogen, I've got my sulfate. Now I'm going to keep sulfate as it is, and the reason I'm going to do that, I've got SO4 here and I've got SO4 there, it's not going to change, so I'm going to make my life easier. Then I've also got K and O and obviously H. So let's count up H's. We've got 3 here, we've got 1 sulfate group goes round together, we've got 1 potassium here and 1 oxygen, and afterwards I've got 2 hydrogens, I've got 1 oxygen, I've got 2 potassiums and 1 sulfate. Well, we're going to need a little bit of work here to try and balance this. If I've got 2 potassiums here, then I must have 2 on this side. And if that gives me 2 here, then I must have 2 oxygens. And I must have another hydrogen. If I've got 4 hydrogens on this side, I need 4 hydrogens on that side. 2 times 2 gives me 4, and 2 oxygens. That's balanced, 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 balanced. So there is my formula. So I know in this reaction that we get our H2SO4 reacts with 2 KOH. So I know that if I've got 1 molecule of this, it will react with 2 molecules of KOH. If I've therefore got 1 mole of this, I know it's going to react with 2 moles of that. Let's have a question. I've got 25 centimetre cubed of 2 molar hydrochloric acid, and that will react with 19 centimetre cubed of who knows what concentration of KOH. Let's work out how much, I wrote HCl, didn't I? H2SO4. There we are. Got 2 molecules of that. So let's work out what that is. So I've got my equation. N equals the concentration times the volume divided by 1000. Let's work out how much sulfuric acid I have. So I've got my concentration, 2 times my volume, 25, divided by 1000. And you'll see I've made my sum easy to work out. Let's do it. So I've got here my 2 molar times 25 mils, all divided by 1000, and that's going to give me 0.05. Now I've said that reacts with 19 mils, so let's rearrange this formula, and we know that the concentration here is going to equal number of moles times 1000 divided by the volume. I know my sulfuric acid, I've got 1 mole reacts with 2 moles. So if I have here 0.05 moles, I didn't write that well, did I? Here we go. I've got 0.05 moles of H2SO4. It's going to react with twice the amount of potassium hydroxide. So that's going to react with 0.1 moles of potassium hydroxide. I've got to have twice the amount of that as that. So now I know how many moles of this I have. 0.1 times 1000 divided by the volume I said, which was 19 centimetre cubed. Let's put that into the calculator. So we've got 0.1 times 1000 all divided by 19. And that gives me 5.26 moles per decimetre cubed of my potassium hydroxide. Oh yeah, worked out quite well really. So a titration can be quite quick. Normally you need to do about 3. I would always do 1 to start with to give me an approximation of where I want to go, and then I will try and do 3 titrations as accurately as I can, and I'm after getting my numbers within about 0.1 of each other. Then I can do the calculations, and that will give me a fairly accurate concentration. So that's looking at titrations. The last little bit that I want to cover is also about amounts of stuff, and that is an interesting little rule, because when we play around with gases, different rules apply. If I want to have a look at some gases, the scientists over the years have worked out that basically the number of moles of gas here equals the volume of the gas, which we measure in decimetre cubed, divided by 24. And this is because that they managed to work out that 1 mole of any gas, no matter what it is, occupies 24 decimeter cubed at RTP, room temperature and pressure. Now, room temperature is fairly easy to try and work out, because all we need to do is grab hold of a thermometer, and we discover that room temperature is about 20 degrees Celsius. Sometimes we work about this in Kelvin. 273 Kelvin equals 0 degrees Celsius, and so we either work at 20 or we could work at 25 degrees Celsius. So 25 degrees Celsius is 298 K, and 20 degrees Celsius is going to be 293 K. No degree sign. Kelvin's an absolute scale. The pressure we measure normally in atmospheres, and this will be 1 atmosphere. We can measure pressure in other ways. We can measure it in pascals, and it's about 101,000 pascals. So we can talk about that. If we want to try and do some calculations with this, it's not that difficult to do, because we might want to find out and work out something. So let's see if we've got so much gas. So let's suppose we've got 25 grams of a gas. Which gas shall we go for? How about oxygen? O2. So what do we know about this? Well, I know the number of moles equals the mass over the relative formula mass. I've got 25 grams here over mR, and if we look up the relative mass of oxygen here is 16, so it's O2, so this is going to be 32. So that tells me how many moles I've got of this substance. Let's put it in the calculator and work it out. So we've got 25 divided by, I didn't need the divide there, did I? Divided by 32. And that tells me I've got 0.78125 moles of oxygen. That tells me how many moles that we've got. So if I want to work out the volume of the gas, it's going to be volume of gas is going to be the number of moles times my volume. Sorry, my volume of gas is going to be number of moles here times here 24 decimeter cubed. 0.78125 times 24. I saved the number on the calculator, so I'm just going to multiply that by 24, and I get out 18.75. So if I've got 25 grams of oxygen, it will occupy 18.75 decimeter cubes at room temperature and pressure. In a similar way, we could work out the mass of a particular gas. So let's suppose we produce some gas. Let's produce 100 cm cubed of a gas. Let's choose what gas it's going to be, and let's suppose I've made some methane, CH4. So I've got 100 cm cubed of CH4. Now, what we first need to do is to work out how many moles of gas that is. So 100 centimeter cubed, so I want to work out the number of moles of gas. That's going to be the volume divided by 24 decimeter cubed. Now this has to be in decimeter cubed, and that's in centimeter cubed. So how many centimeter cubes in 1 decimeter cubed? And the answer is 1,000. So this is going to give me 0.1. So we've now got these in the same units. So let's pop over to the calculator and let's do this sum. So we've got 0.1 divided by 24. And this is going to give me 4.16 recurring times 10 to the minus 3. And we're going to use it in standard form notation. So now I've got the number of moles of gas. Once I've got the number of moles of gas, I want to work out what weight, what number of moles. I want to work out the mass I've got. So number of moles here equals the mass divided by the mR. So let's just write that down. So let's rearrange that to work out the mass. It's going to be N times the mR is going to give me my mass. I've got my number of moles. I'm going to times that by the relative formula mass of methane. Carbon is 12. Hydrogen here is going to give me 4. So we've got there 16. So it's going to be my 4.16 recurring, which is why I've left it on the calculator, and I'm going to times that by 16. So on the calculator we left that there, and we simply want to times that by 16 to give me my mass, and my mass is going to come out at 0.06 recurring grams of methane. And there we've worked out some volumes of gases. So that's taken us through over the last few sessions looking at calculations, and these are very popular in the exams. Why? Because they can test you on them, and they're also testing you a bit on your maths as well, although the sort of maths we're only doing are simple fractions that you can do on the calculator, which is why I've been using the calculator for each of these. Thank you for watching. I hope you've learnt something with this. If you liked what you're watching and you found it useful, then please feel free to subscribe, and I will see you next week when we'll start having a look at some chemical changes and look at the reactivity series of metals, and perhaps some more as well. Until then, stay safe. Bye bye.